Thanks for the invitation to speak. I'll be discussing work done in collaboration with Shivaji Sondhi at Princeton, and this is the paper that's most relevant to today's talk. So our central goal in condensed matter is to characterize the different possible phases of matter, and we usually deal with equilibrium phases, and in that context we characterize phases by the long-distance behavior of correlation functions in their low-lying states. So, for instance, we distinguish paramagnets from ferromagnets by saying that paramagnets have short-range correlations and ferromagnets have long-range correlations. So, until recently, that was what people would talk about in this context. But with many-body localization, we have a new idea, and that's the idea of an eigenstate phase. So within an eigenstate phase, all of the eigenstates of a many-body Hamiltonian have some quantum order in common, like long-range order or string order or edge modes. And across an eigenstate phase transition, we have a sharp change in these eigenstate properties. Now, that probably sounds quite esoteric, but these eigenstate phases also have very concrete dynamical signatures that we can see in an experiment as well. It's just we characterize these as eigenstate phases for theoretical reasons. Like it's neater to think about it that way. So both of the problems I've just mentioned, the equilibrium traditional equilibrium problem and the MBL problem, involve characterizing the eigenstates of local time-independent Hamiltonians. But in today's talk, we'll be considering maybe a slightly richer question, which is what new phenomena or phases can arise in driven systems. And by driven system, I mean a system that does not have a time-independent Hamiltonian. The Hamiltonian depends on time. Is there a sharp notion of phase in such situations? Is there a generalization of eigenstate phase? And most importantly, what are the telltale dynamical signatures of such phases? So it turns out that rather surprisingly, for time-dependent Hamiltonians, which vary periodically in time, we call those flow K Hamiltonians, there is indeed a sharp notion of phase of matter. But it seems that for there to be a sharp notion of phase of matter, you need disorder in these systems, and I'll explain some of this shortly. And everything I say today will build on some earlier work by my collaborators. So how do we characterize one of these driven phases of matter? Well, it'll turn out that these driven phases of matter are characterized by the long-time behavior of local observables. And this long-time behavior is in turn determined by the eigenstate properties of this flow K unitary. So much as in the many-body localized problem, we characterize the phase by looking at all of the eigenstates of a many-body Hamiltonian, in these flow K phases, we characterize the phases by looking at the eigenstate properties of this complicated many-body operator. And this is just the time-ordered exponent of the time-dependent many-body Hamiltonian over one period. Okay, so let me say a little bit more about why we need to introduce, or appear to need to introduce, disorder in this setting. So let me tell you what seems to be a fact about clean interacting flow K systems. So if you have a many-body Hamiltonian that depends on time periodically and it's interacting, it seems as though such systems, we say, thermalize to infinite temperatures. So what that means is that at very, very long times, local observables have trivial dynamics. So let me flesh that out a little bit more. So this red curve, this is very complicated computer graphics. This red curve is what I mean by thermalized to infinite temperature. At long times, this local observable just goes to its trace average. So why do I call this heating to infinite temperature? Well, in more traditional ETH systems, we know that if we start with some initial state and we look at the long-time behavior of a local observable, at long times its value is determined by Gibbs ensemble with a temperature that's determined by the initial state. And you can see you can get from this ETH picture to this clean flow K picture by simply setting the inverse temperature to 0. These two formulae coincide if beta is equal to infinity. So when I say that clean interacting flow K systems tend to heat to infinite temperature, I'm making a statement about their long time behavior. Their long time behavior is determined by an infinite temperature ensemble. But it turns out that if you now introduce disorder, you can disrupt this runaway heating to infinite temperature. And in the systems I'll consider today, these disordered flow case systems, at long times, local observables can show non-trivial oscillations, which are universal and robust and do not die away in the thermodynamic limit. And this is a sort of boon to experimentalists, because it means that if you can probe the system for long enough and measure these observables, you can distinguish different flow K phases. And I'll talk about that in a bit more detail. So the upshot of what I've just said is that there is indeed a sharp notion of phase of matter for driven systems. It seems that we need disorder, but okay, that's experimentally doable in certain setups. What I'll focus on today is a new class of disordered flow K symmetry protected topological phases, and I'll focus on 1D in particular. And I'll tell you about classification of such phases. And I'll also say what you might see in an experiment for a particular example of such a phase. Let me just mention as an aside, we have a similar classification scheme for flow K phases with long-range order, and this relates to the time crystal story. I'm not going to talk much about the time crystal story today because there were a heck of a lot of talks on it just a few weeks ago. And I believe there'll be at least one talk the rest of this conference about that. So, I mean, let me not talk about that, but let me highlight it's very interesting and you should read about it. Okay, so that's today's talk. So let me give you a brief overview of how this 1D SPT classification works. The input for the classification is some global symmetry group, G. It might be Ising symmetry or time reversal or something like this. All I'll ask today is that it's finite and abelian. And another part of the input is some symmetric 1D flow K time periodic Hamiltonian, which preserves this global symmetry. And we'll be interested in the properties of this operator, as I was saying before. So, moreover, I will specialize to a situation where H is so disordered that this flow K unitary has a complete set of local conserved quantities in the bulk. And I mean, I haven't told you that you can make this. You can always make a Hamiltonian sufficiently disordered such that you have a complete set of local integrals of motion in the bulk. But this. There are various analytic arguments, for instance, by Dima, and numerics which support the idea that if you do make H sufficiently disordered, you can get this complete set of conserved quantities in the bulk. So our classification scheme asks what properties of this flow K unitary are robust to sufficiently small perturbations to U, which preserve the global symmetry. And what the classification puts out is the following. What we show, and I guess I can take this as a question at the end if you're interested in more of the details, is that this flow K unitary can always be decomposed in a certain canonical form into two parts. There's e to the minus if VL VR. This f is some local functional of the bulk conserved quantities, and in fact just looks like an SPT Hamiltonian. And these VR operators are unitaries that are localized near the edges of the system. And they can be chosen to commute with the bulk Alberts and F in particular. So we argue that you can always decompose this flow K unitary into these two types of parts, these edge parts and this bulk part. And correspondingly, the classification of these SPTs has two parts. The first part of the classification asks what kind of SPT order is encoded in this bulk Hamiltonian. And the second part asks what the symmetry properties of these VL-VR operators are. And it turns out that this is the data that is robust to symmetric changes to the Hamiltonian. And so our classification has this product structure as a result of that. But something that's quite nice about this interpretation is that it tells you that all of these MBL flow K drives can be thought of physically. You can always rearrange them so that they look like a two-step process. In the first part of the process, you drive with just a time-independent MBL SPT Hamiltonian, and in the second part of the process, you do something at the edges. And it turns out you can always think of this as transporting a charge, or transporting a charge under the global symmetry from the left edge to the right edge of the system. So I realize I haven't gone over that in enough detail so that everyone will follow. I just wanted to give some intuition for what these things look like. So what I'll do now is just give some examples of how these flow K SPTs have a richer classification than SPTs that we know from equilibrium and MBL. Yes.
Just to make sure I understand. So the blue part, the bulk part, has the same classification as a non-driven system.
Correct.
Exactly.
Correct.
So the only extra classification is whether there is a non-trivial edge pumping.
Exactly. Exactly. Although that wasn't clear to us at the beginning, although the answer ended up being simpler than me. Okay, so let me give some examples, and I'll make some. Let me give some examples. So let's talk about one-dimensional system in class D. When people say class D, what they mean is 1D superconductor which has no symmetries other than fermion parity symmetry. In the undriven context, such systems have a Z2 classification. So there are two possible types of SPTs with just fermion parity symmetry in 1D, and these are known variously as either the Kitaev chain, that's the one with Majoranas at the end, and just a trivial chain with the on-site chemical potential, that's what we call the trivial state. So there's a Z2 classification in this part. That's what I mean by CL equals Z2. So it turns out that in the flow K setting, the symmetry is enriched. Sorry, this classification is enriched. We get the Z2 from the undriven classification, the Z2 here, and then we get a pump charge, which can take one of two values. And this corresponds to the fact that for this flow K drive, you can, in the bulk, either evolve with a Kitaev Hamiltonian or a trivial Hamiltonian. And then at the edge, you can either do nothing, or you can transport a fermion odd charge from the left edge to the right edge. And so that's where the Z2 cross Z2 comes out with. And reassuringly, this agrees with various non-interacting results on driven Kitaev chains. But actually, it becomes more interesting when you consider other classes. And because this classification is intrinsically interacting, it differs from some of the existing non-interacting results. So I'll just give an example here, which is class BD1. So you can think of this as a 1D superconductor with only fermion parity and time reversal symmetry. And for interacting systems, in the undriven setting, this is known to have a Z8 classification. It's quite a famous result. It's associated with Kitaev, Witkowski, and yes?
Just to the previous, so you have Z2 cross Z2, but if you are in a trivial state, you don't have edge modes, what do you transport in your...
You don't transport anything. So the second Z2 corresponds to either transporting something fermion odd or not transporting anything at all.
Yeah, but if you have no edge states, how can you transport or not transport? There is simply no transport, right?
I don't understand.
Okay.
Sorry.
Suppose your bulk is trivial.
Yes.
So you have this Z2 classification. So
yes.
Suppose the bulk is in the trivial
yes.
state, then there is still the freedom of either
yes.
transport
yes.
or not.
Yes. I can show you a specific drive that'll do that for you. And indeed, in that case, you get in that case, you do get edge modes. We'll see a very similar example later in this talk, and hopefully that'll. If you do a Jordan-Wigner transformation of that example, it gives exactly what you're asking for.
Can you get Marx phase from this, where the bulk is trivial and the edge has...
It's a similar idea in so far as in that case you can decompose the flow K unitary as something that acts like a trivial Anderson insulator in the bulk and something which just acts like a momentum operator on the edge. So it's a similar idea, but not exactly the same. Sorry, there was another question.
I was going to ask, could you repeat the question?
Could we possibly wait till the end of the talk and then? Because I think I'm going to go over some of these again shortly. So. Okay, so what I was saying is there's also a situation which has fermion parity and time reversal symmetry, and in the undriven setting this has a Z8 classification. And it turns out that in the flow case setting this Z8 classification goes to something like a Z8 cross C4 classification. So that's a new result. As I understand it, in the non-interacting classification this just becomes a Z cross C. So it's different on two counts. One is that Z is broken to Z8 for the undriven part, and Z is broken to Z4 for the driven part, roughly speaking. So that's a new set of states. Let me just comment on some further results. I'll say this very briefly. For bosonic theories with G abelian and finite, the classification has a nice structure. I won't explain what these mean. If you know this, you'll know it, and if you don't, I guess you won't. Let me comment on some follow-up work, which is that basically what our paper shows is that the classification can be interpreted as extending the symmetry group of the problem to include time translation symmetry. And that's a very useful observation because it means that you can just put this extended symmetry group into the existing SBT classifications and it spits out an answer for you automatically. And so for that I'd highlight some work by Elsa Naik and Potter, Marimoto and Vishwanath. Okay, so now I'll do one example to death. And it's, I think, an example which is relevant to experiment. I think that there was just a paper a couple of weeks ago by the Harvard, Berkeley, Mafia on this one. And a realization of it in Rydberg systems. So let's just consider simplest possible non-trivial group, C2. So Ising symmetry. And let's realize this. Sorry, how much time do I have left? Just 11 minutes, good. Okay. So let's consider a system with Ising symmetry, and let's think about realizing this system on a Hilbert space with just spin halves on a lattice. And we'll realize the Ising symmetry is a big product of Pauli sigma X matrices. So that's what I mean by that. So in the undriven setting, in fact, there's just a trivial SPT classification for these phases. There is no Z2 bosonic SPT in 1D. So that's what I mean by Z1. Okay, there's only one state here. Here's an example of a undriven trivial SPT with Ising symmetry. It's just a paramagnetic Hamiltonian. It doesn't have any edge modes that are protected, nothing like that. So that's what I'm saying here. So, but it turns out that the flow K classification for such systems is non-trivial. And in fact, there are two possible flow K SPTs. The trivial one, which looks something like this, or behaves very similarly to this model, and a non-trivial one, which actually has an edge mode. Okay, so we'll construct that shortly. And the fact that there's a Z2 classification corresponds to the fact that, in this case, the pump charge can take just one of two values, because they're just two representations for Z2, either Ising even or Ising odd. So in one case, you, I think I'll say that shortly anyway. Yeah, okay. So let me give some examples of flow K unitaries in these two phases. So I'll call the trivial phase, I'll either call it trivial or the zero paramagnet. The non-trivial one, I'll call the 0 pi paramagnet, or non-trivial. Okay? So here is an example of a flow K unitary in the 0 paramagnet or trivial phase. It just looks like driving with a paramagnetic Hamiltonian, and it doesn't have any edge modes. And here is an example of a 0 pi paramagnet. Floquet unitary on a system with some boundaries. So really the only difference between these two things is the fact that in this case you do something Ising odd at one of the edges and Ising odd at, you do something Ising odd at each of the edges, but on net you've done something that's Ising even. In particular, you can think of this as hopping an Ising charge from the left edge to the right edge. Okay. So let me just engineer an Ising symmetric drive, which so an Ising symmetric Hamiltonian, which gives rise to this drive. So we'll do it using a two-part drive. So consider the following piecewise constant Hamiltonian corresponding to the 0 pi paramagnet. For the first part of the drive, for time t1, you just drive with this trivial paramagnetic Hamiltonian. And for the second part of the drive, for a duration of total pi over 2, you drive with this ferromagnetic Hamiltonian. Okay? Well, actually, anti-ferromagnetic, I guess. So on a system without any boundaries, you can construct the corresponding Floquet unitary. This component of the Floquet unitary just comes from driving with this. This component of the Floquet unitary comes from driving with this. Okay? It turns out that using an algebraic identity, I'll show you on the next page, that on a system without boundary, this just simplifies to something really simple. You just drive with this paramagnetic Hamiltonian. But on a system with boundary, you accumulate some charge at the edges, Ising charge at the edges. And and so you get this Floquet unitary I spoke about on the other side. And the relevant identity is this. You know, if you have a unitary of this form, you can write it as a product of unitaries. Then you can use this identity for operators that square to 1 to show that this is equal to this up to a phase. Then you do this big product and you find that lots of the factors cancel except the very end parts of it. Okay. So I've given you a very specific example of a drive protocol, but it turns out that this is just one example of a Hamiltonian in a larger symmetry-protected phase. So what I mean by that is you can take this particular Hamiltonian that I gave you before and you can perturb it by anything that's local Ising even and preserves the driving period, provided it's sufficiently small, and basically you can continue to have these edge states. The long time behavior I'll talk about on the next page. So the basic physics of this model is insensitive to such small perturbations. Yes?
How do you ensure small perturbation has the preheating?
Sorry?
Like small perturbation can be preheating.
I've that paramagnetic Hamiltonian I had on the previous page, I'm imagining it was really, really strongly disordered.
Yeah. Any small perturbation would provide.
Yeah. Provided my starting point is sufficiently disordered such that small perturbation does not lead to heating. Okay? Okay. So, but what I'll do now is I will explain some of what I think will be the clearer experimental signatures for this phase using the specific drive I constructed, and you'll just have to take it on trust that they hold with only minor modifications for this more general set of models. And that's something that at least can be numerically verified, and we can come up with plausible reasoning for why it should continue to be true. Okay, so let me just do one thing. So let's just consider operator x1 at the left edge. Okay, so Pauli matrix on the very first site at the left edge, and let's consider how this operator evolves under the Floquet unitary reconstructed. So you can see that as an operator equation, as you evolve this operator stroboscopically, it just flips sign every period. Okay? So that's quite a powerful thing, having an operator identity like this, because it shows you that if you just take any old initial state, provided that initial state has a non-trivial expectation value for x1, it'll oscillate in time with a period 2t, because this equation only comes back to itself when n changes by an even number. Okay? So you can go from this statement to a much more powerful statement, which is true generally in the phase, which is that if you look at an edge observable in this non-trivial 0 pi paramagnetic phase, this really is a cartoon picture. The numerics are rather messier than this, but I just want to illustrate the point. which is, yes?
If I understand correctly, for you, periodicity of the drive doesn't play any role, right? So it's not really a flow case system.
It's a flow case system.
No, but you don't care, I think, if it's a flow case system.
If I change the
Period
fundamental...
changes, right, so you just sort of measure time in cycles and everything stays the same, right? So, I mean, if the drive...
If I break the T periodicity, this picture will no longer hold.
What
For instance, if I break the T to 2T periodicity, this picture will no longer hold.
Maybe what will break in the periodicity?
Well,
you
this...
just use this simple identity, which is after one sort of...
So what happens if you break the periodicity? You very suddenly change the definition of flow K unitary, right? So let's suppose...
You measure time in cycles.
Yeah, but you change the unit of that cycle from T to 2T. And I'm plotting this picture over here in units of T. So what you'll find is if you very weakly break it to 2T, you'll just be sampling these points. And this curve will just look flat.
It means you have irregular triangles, but you will still have perfect triangles.
Let me explain this slide first, and then maybe we'll come back to it. Yeah, okay. So here I'm just telling you something that distinguishes the zero paramagnetic and the pi paramagnetic phase. If you look at an edge observable, and you, let's say, probe it stroboscopically at multiples of the underlying flow K period, you'll find that in the zero paramagnetic phase, these curves just settle down and become constant. Whereas in the zero pi paramagnetic phase, they show this persistent oscillation. This is for edge observables. In the bulk, in fact, you can't distinguish between the two phases using this stroboscopic measurement. And they all in both phases, it ends up flatlining like this in the bulk. Okay, so the conclusion here is that there is a sharp notion of phase of matter in these periodically driven disordered systems, and these various periodically driven phases are distinguished by the long time behavior of local observables. For these SPT phases, they're distinguished by the behavior of observables at the edge. In more general phase, in other phases like this time crystal phase that I briefly alluded to, they're distinguished by the long time behavior of bulk observables. So what I did in this talk is I showed you briefly, gave you a basic idea how the classification of these 1D SPT states works. And yeah, that's it. Let me just the various papers on related work, and if you want any of the references, they're here. Yeah. So yeah, that's what I want to say.
Questions? Yes.
Yeah. This one?
Yeah.
Yeah.
So I just suppose I don't have a flocky, I just do a quench, and sort of UF will evolve in time. So as a function of time, won't I get like a similar periodicity if I wait right amount of time after the quench, X1 will come back to itself, or this is not true?
Wait, sorry. So what exactly are you picking as your Hamiltonian?
Well, you had two terms. So
Yeah.
one of them is initial state and one of them is Hamiltonian. And if you just wait sufficient amount of time, the system will sort of periodically go back to this.
Wait, you're proposing to use the same Hamiltonian as I'm using?
Yeah.
Okay. So the same two-part Hamiltonian?
Yes.
Okay. And so what are you now saying?
I'm just asking if you just do a quench to this new Hamiltonian,
Oh,
and
you do
wait
a
is a
quench.
function of time, right? So won't you see the same periodicity, but
Yeah,
as a
okay.
function of waiting
Yeah,
time?
so what I'm saying here does not depend on the initial state, and I think what you're suggesting is starting with an initial state, which you get by hitting it with a, you're imagining imagining driving with one type of Hamiltonian and then changing to this flow K Hamiltonian,
Not even okay, just a quench. But as a function of waiting time, won't you get this revivals? Well, maybe it was too fast.
By exactly the two parts.
Yeah, exactly. But I'm just saying you just quench to a different part and wait. And as a function of waiting time, won't you see this revivals time after time?
So with the period which is given by the 2 pi universal omega.
Right, exactly. Yeah, exactly. That's what my question is.
Maybe.
Okay. So I still don't. I have to admit, I still don't understand the question, but maybe you can help me. So, okay. So I wrote down a particular Hamiltonian H0 pi, which is this two-part thing. Now you're imagining starting with a different Hamiltonian and somehow changing that Hamiltonian to this Hamiltonian?
No, in your Hamiltonian you had two terms, right?
Yes.
So one was x, one was z0.
Yes. Yes.
So I'm starting from, say, eigenstate where x takes a particular value, and then you evolve with the z Hamiltonian. So my question is, for wait certain time.
So you're starting with a particular eigenstate, which is an x eigenstate.
For example.
Okay. What I said over there was basically independent of the initial state. Let me just emphasize that.
No, I understand.
Okay.
If revivals occur in the same period, it also doesn't depend on initial state. Maybe we can talk later.
No, it's okay. I'm just trying to understand. Okay, so you're imagining driving with this Hamiltonian and starting in an x product state initially. Okay.
Right, the second line. Second line is say the Hamiltonian, yes. Just
Oh, you want to evolve just with this
yeah, that's what I'm saying.
paramagnetic Hamiltonian, not with this two-part drive.
Right.
Okay, so I see. Right, so you just want to drive with one Hamiltonian, starting from an x state. Okay, so first of all, this is not disordered, and so I think that it's whatever statement I make is going to. I think this is depends on what you're allowed to add, but if you allow yourself to add even a weak driving term with interactions, the system is going to be unstable to heating up.
I think even regardless of adding this, when you add this SZ term, things will just entangle more and more, and there will not be any oscillations. Things will completely dephase. I think in order for them not to dephase, you need another term that periodically brings, switches the direction the spins are going, so that.
Well, this one in particular is not going to spread very far because this is.
It will just
X1 will
dephase.
just spread to one of two sites. Because this is fully local integrable Hamiltonian, so it'll just spread between your in general x1 as a function of time will look like some superposition of I guess like 15 possible products of Pauli matrices. I know I'm mixing notation here, but this look like something like this.
Maybe we can talk about this later.
Okay.
Just if you consider systems which don't heat up, it's kind of easy to see that the flow K is nothing special in periodic driving. So we say that flow K is important because we can define flow K Hamiltonian and so on. This is just a language, and it's language which is convenient to us. But we can work with these unitaries to begin with. And typically, flow K leads to heating, then any unitary leads to heating, and then we're saying, system heats up. But if it doesn't heat up, actually periodicity is not that important. In all the systems, like band models or whatever, you can consider perfectly aperiodic driving, and you will have exactly the same properties, like at least many of the same properties, topological or whatever, they will survive. They don't rely on the periodicity.
But hang on, if you have completely random dynamics, I thought that you expect unbounded entanglement growth in these situations like ballistic.
Let's continue this later. I think actually periodic driving is crucial because it adds a symmetry to a problem. It's discrete time translation, and things will be completely different without it. So it's at least from the topological perspective and symmetry breaking perspective. But okay.
Sorry, so this is maybe a silly question. I just want to orient myself. So am I correct that if I take your model to spin, whatever it's called, paramagnet, and I do a duality transformation, I get one of these time crystals?
Yeah.
Okay.
Right.
So then what are the physical consequences of picking one versus the other?
Well, in the time crystal case, these statements about 2T oscillations hold for bulk observables, whereas in the 0 pi paramagnetic case, those statements hold for edge observables. And
so it seems like another difference is also one of them is robust only against symmetry respecting perturbations. The other one is robust to everything.
Yeah, but because under this duality transformation, symmetry odd operators end up getting like a non-local string attached to them.
Thank you.
Yeah, I just want to come back to, I think, the questions that Anatoly was asking more or less. I mean, how do you avoid heating?
In this case, I believe we're avoiding heating by adding strong disorder.
But, okay, is there an argument that that does the job completely?
Well, I mean, there are some sort of semi-analytic arguments, I think, from Dima, that at least at high enough frequency, these systems continue to be localized, many-body localized.
For infinitely long times, all right?
I don't know the statements of their proof well enough to know exactly what they break down. Maybe Dima can answer that question better than I can.
So you can show that if driving frequency is high enough, right? So you can do a series of local unitaries, and essentially you bring the problem back to the static many-body localization. So the statement is that if your driving frequency is high enough and driving amplitude is not super high but finite, you can still construct a complete set of local integrals of motion, right? So and you never heat up essentially, right? And you can make it pretty much rigorous. I mean, we didn't bring it to a level of a proof, but you can.
So there's a threshold frequency, or you have to take something to like the frequency to infinity to show?
No. There is a finite threshold frequency which you can find, and then there are also where the story is a bit less clear is the limit of low driving frequencies. Here really there are qualitative arguments that you get Landau-Zinner transitions which are mixing transitions, and then you argue that at low enough frequency there is always delocalization, no matter how small the driving amplitude is. Right, but there the story is really qualitative. So I think the high frequency part and the existence of the MBL phase and driven systems is clear. But this delocalization at low frequencies is quite interesting in itself.
So there's really a phase transition at some finite frequency.
Yes. That's
and the other interesting property. Well, okay.
So more questions? To Court.
Yeah. So what if you have an open system? How about the open system?
I'm not sure. Sorry. I mean, I think there's some interesting work done by people at Station Q where they consider stabilizing time crystal-like phases by coupling even clean systems to a cooling bath. I think that's an interesting thing that one can do. Otherwise, I think this is pretty similar to the question of asking how MBL delocalizes when you couple it to a bath. But I don't have very much. Sorry, how stable MBL is to coupling to a bath, and I'm afraid I don't know very much about that.
Actually, Kurt, so did you think at all about the case of quasi-periodic driving? So would it lead to richer structure, even if you forget about this question whether many-body localization can survive in the presence of quasi-periodic drive?
That sounds like a very interesting question. I mean, but I don't know what the answer is. There's a vague intuition that if I have two different frequencies, eventually it'll heat up because I can have. If I consider two generic frequencies, I can have transitions anywhere across the, on the circle of quasi-energies. But other than that very poorly developed intuition, I have nothing to say about that.
Well, that's maybe not always like that, right? Because you know that if you take single particle systems, and that's the case that's been studied, and that's where people did this quasi-periodic driving. So if you take
which work is this one?
If you take we can find the reference, but so the idea is that if you consider kicked rotor, but you kicked it at several different frequencies, this becomes effectively problem of Anderson localization in higher dimensions, right?
Yeah.
In the energy space.
So
people studied transitions. Essentially you can study Anderson transition and so on.
But in energy space.
In energy space, yes.
Okay. All right,
There were experiments.
That seems like quite a. I'm not saying that's not interesting, but it seems like quite a different problem. Given that.
Right. But my point is that there is localization in that case, despite the fact that you have multiple driving frequencies which are incommensurate.
But like it's localization in energy space, not.
Right.
Yeah.
Which means no heating.
Yes, right. So if you have no heating, maybe you don't need many-body localization in order
I
to
see, sorry.
stabilize these phases.
You're not talking about, you're not talking about localizing MBL necessarily, but you are
Not
talking
necessarily.
about localizing in energy.
Yeah,
Okay,
suppressing heating.
I see. Okay, yeah, that's a cool idea.
Actually, if I'm not mistaken, in the single particle case, you don't even need incommensurate drive. There is only one drive, and it's incommensurate with some intrinsic time scale. So in principle, you can imagine, and I think Victor has some paper about this, maybe you can comment, where you get localization in energy space just by periodic driving. So I wonder if you can get two things at the same time, both localization in energy space that prevents heating, and then topological phases because you've not heated. So.
And so you expect that when you have this localization in energy space, you can. Does that tell you that there's now this emergent conserved quantity that looks something like a local Hamiltonian? So that's basically it. So
maybe I
that
don't.
these
It's
systems
not
with
clear.
incommensurate frequencies might have effective Hamiltonians.
Yes. But even if you don't, if you
but
can't,
if that is the case and they do just look like normal Hamiltonians, then doesn't that reduce to classifying local Hamiltonians?
well, maybe
maybe,
because
yeah,
of
there are
driving,
two
there is new symmetries like discrete time translation. So
Sure. No. I don't know what I'm talking about.
any more questions? So if not,
I just want to comment on this periodic driving thing. So in this periodic driving case, if you have localization in energy space, then you don't have localization in real space. So the conserved quantity just shift between either energy space or real space. So
All of these arguments rely on MBL. All of the classification arguments rely on localization in real
so the
space. Although that could just be a limitation of our classification scheme.
the periodic, if you have localization by periodic driving in energy space, then I think you lose the local integrals of motion in the real space. So it just migrates between one and another.
okay. If there are no other questions or comments, I think we can go for thank Kurt again and go for morning break.